At the deepest level of existence, quantum physics reveals that reality is not built on certainty, but on probability, a discovery that quietly reshaped how humanity understands the universe. Before this realization, the dominant view of nature was deeply rooted in classical physics, where every object had a precise position, a definite speed, and a predictable future. If all forces were known, the universe appeared solid and dependable, unfolding like a perfectly designed machine. Quantum physics did not overthrow this picture loudly or dramatically. Instead, it gently eroded its foundations, replacing absolute predictability with a calm field of possibilities. When scientists began probing matter at extremely small scales, they expected to find smaller versions of familiar objects, tiny particles behaving like miniature billiard balls. What they found instead was something profoundly different. Electrons, photons, and other fundamental entities refused to behave as solid points moving along clear paths. Experiments showed that these entities could not be described by exact values alone. Instead, they were best represented by mathematical expressions that described likelihoods. Rather than saying where a particle is, quantum physics speaks of where it is most likely to be found. Reality, at this scale, exists not as a fixed fact, but as a spread of potential outcomes. This probabilistic nature is not due to limitations in technology or human knowledge. Even with perfect instruments, quantum theory suggests that nature itself does not assign definite values until interactions occur. The wave function, a central concept in quantum mechanics, encapsulates this idea. It does not describe a particle as a single object in a single place, but as a cloud of probabilities gently spread across space. Each point in this cloud represents a chance, not a certainty. When a measurement happens, the cloud does not gradually narrow. It abruptly resolves into a specific outcome. This sudden resolution is not random chaos, but structured uncertainty, governed by precise mathematical rules that determine how likely each result is. What makes this idea so profound is that it suggests uncertainty is not a flaw in our understanding of reality, but a fundamental feature of reality itself. The universe, at its core, does not commit to one outcome until interaction demands it. This challenges the deeply ingrained human desire for certainty and control. Yet there is something quietly comforting in this view. Reality is not rigidly predetermined. It is open, flexible, and responsive. The future is not a single straight line, but a range of possibilities, gently narrowing as events unfold. The famous double-slit experiment illustrates this idea with remarkable clarity. When particles such as electrons are fired toward a screen with two narrow openings, they produce an interference pattern, a result traditionally associated with waves, not particles. Each electron seems to pass through both slits at once, spreading its probability across multiple paths. Yet, when detectors are placed to observe which slit the electron goes through, the interference disappears, and the electron behaves like a localized particle. The act of measurement does not merely reveal a hidden reality. It participates in shaping the outcome. The electron does not choose a definite path until the situation requires it to do so. This behavior forces a reconsideration of what it means for something to exist. In classical thinking, existence is tied to definite properties. An object exists because it has a position, a mass, and a trajectory. Quantum physics suggests a softer definition. At the fundamental level, existence can mean a set of possibilities, a readiness to become something specific when the right interaction occurs. Reality, then, is not a static collection of facts, but an evolving process, where potential is just as real as outcome. Probability in quantum physics is often misunderstood as mere randomness, but this interpretation misses its subtlety. Quantum probabilities are not arbitrary. They follow precise patterns and conservation laws. Over many experiments, outcomes form stable distributions that can be predicted with extraordinary accuracy. What cannot be predicted is the result of a single event. This combination of statistical order and individual uncertainty gives quantum reality its distinctive character. It is neither chaotic nor fully determined, but balanced in a delicate middle ground. This balance has philosophical implications that extend far beyond physics. If reality itself is probabilistic, then determinism loses its absolute authority. The idea that the future is completely fixed by the past becomes difficult to maintain. Instead, the universe appears to allow room for novelty, emergence, and genuine openness. This does not imply that anything can happen, but it does suggest that not everything is pre-written. There is space for creativity in the fabric of existence itself. The probabilistic nature of reality also reshapes how we think about causality. In everyday experience, causes lead to effects in a straightforward way. In the quantum realm, causes influence probabilities rather than dictating outcomes. An interaction sets the conditions under which certain results are more likely, but it does not guarantee a specific result. This softer form of causation aligns more closely with how complex systems behave at larger scales, where patterns emerge from many interacting factors rather than simple chains of cause and effect. As quantum ideas gradually permeate modern technology, their practical significance becomes undeniable. Devices such as lasers, semiconductors, and magnetic resonance imaging rely on quantum principles, including probabilistic behavior. These technologies work not in spite of uncertainty, but because of it. Engineers design systems that harness probability, guiding it into reliable patterns. This demonstrates that uncertainty does not undermine functionality. It can be a source of stability and precision when properly understood. Beyond technology, the probabilistic nature of reality invites a quieter, more reflective attitude toward existence. If the universe itself operates through probabilities, then uncertainty is not something to fear or eliminate entirely. It is woven into the structure of being. This perspective can soften our relationship with the unknown. Instead of demanding absolute answers, we can learn to appreciate ranges, tendencies, and possibilities. Knowledge becomes less about domination and more about alignment with how nature actually behaves. At a deeper level, probability suggests that reality is relational. Outcomes depend on interactions, contexts, and conditions. Nothing exists in complete isolation with fully defined properties of its own. Each event arises from a network of influences, converging to produce a particular result among many possible ones. This interconnectedness challenges the idea of independent, self-contained objects and replaces it with a vision of reality as a web of relationships, gently shaping one another. As scientists continue to explore the quantum world, interpretations differ on how to understand probability. Some views suggest that all possibilities exist simultaneously in branching realities, while others maintain that probability reflects an inherent indeterminacy in nature. Despite these differences, all serious interpretations agree on one point. Probability is not merely a tool for dealing with ignorance. It is an essential feature of how the universe operates. In this light, reality appears less like a finished sculpture and more like a flowing stream, constantly forming and reforming itself. Each moment carries multiple futures within it, only one of which becomes actualized through interaction. The present is not a sharp point separating a fixed past from a fixed future, but a gentle transition where possibilities become facts. This vision aligns well with a calm, contemplative understanding of existence, where change is natural and uncertainty is not an enemy. To rest with this idea is to recognize that certainty has never truly been absolute, even in everyday life. Quantum physics simply makes explicit what was always quietly true. The world is not a rigid structure frozen in time, but a living process. By revealing that probability lies at the heart of reality, quantum physics does more than revise scientific equations. It offers a subtle lesson about existence itself, that openness, flexibility, and potential are not signs of weakness, but fundamental expressions of how the universe comes to be. At first glance, the idea that observation plays a role in shaping physical outcomes feels strange, almost unsettling, because it challenges one of the most deeply held assumptions about reality, that the universe exists in a fully formed way, entirely independent of whether anyone looks at it or not. For most of human history, this assumption felt not only reasonable, but obvious. Mountains stood whether or not they were seen, planets moved whether or not they were watched, and atoms, once discovered, were expected to behave the same way. Quantum physics quietly but firmly disrupted this picture, revealing that at the most fundamental level, the act of observation is not a passive window into reality, but an active participant in how reality unfolds. This idea did not arise from philosophy or speculation, but from careful experiments that repeatedly produced results no classical explanation could account for. When scientists began studying light and matter at very small scales, they noticed a persistent pattern. Particles behaved differently depending on how they were measured. The behavior did not change because of human intention or consciousness, but because measurement itself is a physical interaction. To observe something in the quantum world is to interact with it, and that interaction cannot be separated from the outcome. One of the most striking examples comes from experiments where particles display both wave-like and particle-like behavior. When left unobserved in certain ways, particles spread out like waves, producing interference patterns that suggest they travel along multiple paths at once. When observation is introduced to determine their path, this wave-like behavior disappears, and the particles behave as localized objects. The same system, under different observational conditions, produces entirely different physical outcomes. This does not mean the particle is deciding how to behave, but it does mean that its behavior is not fully defined until the interaction takes place. What quantum physics reveals here is subtle but profound. Properties such as position, momentum, and energy are not always fixed attributes waiting to be uncovered. Instead, they can exist in a state of indefiniteness, becoming definite only through interaction. Observation, in this sense, is not about a conscious mind looking at something, but about any process that forces a system to settle into a specific state. A measuring device, a detector, or even interaction with the surrounding environment can serve this role. The universe does not reserve this effect for humans. It happens everywhere, constantly, as systems interact. This reshapes the concept of objectivity. In classical physics, objectivity meant that properties existed independently of how they were measured. In quantum physics, objectivity is more relational. Outcomes are real and measurable, but they are tied to the specific context in which measurement occurs. Change the context, and the outcome may change, even if the underlying system remains the same. Reality, at this level, is not a single rigid structure, but a set of potential outcomes shaped by interactions. This idea becomes even more striking when considering experiments involving entangled particles. When two particles become entangled, their properties are linked in such a way that measuring one instantly influences the outcome of the other, no matter how far apart they are. The act of observation on one particle does not send a signal faster than light, but it does define the outcome for both particles at once. Until measurement occurs, the system exists in a shared state of possibility. Observation resolves that shared uncertainty into a concrete result. Here, observation does not create reality out of nothing, but it selects from among the possibilities allowed by the system. This distinction is important. Quantum physics does not claim that the universe waits for human awareness to exist. Rather, it suggests that certain aspects of reality are fundamentally undefined until interaction occurs. Observation is a process of selection, not creation, yet without that selection, the outcome remains open. This challenges the comforting idea of a fully determined universe unfolding along a single, inevitable path. Instead, quantum physics presents a reality that is partially open, where multiple futures coexist as possibilities until circumstances narrow them down. Observation is one of the key mechanisms by which this narrowing occurs. Each interaction gently shapes the flow of events, guiding potential into actuality. The role of observation also forces a reconsideration of the boundary between observer and observed. In everyday experience, we tend to see ourselves as separate from the world, standing outside it and looking in. Quantum physics dissolves this clear separation. To observe is to interact, and to interact is to become part of the system, even if only briefly. There is no perfectly detached viewpoint from which reality can be seen without being influenced. Every measurement leaves a trace. This does not mean reality is subjective in the sense of being dependent on personal beliefs or perceptions. The outcomes of quantum experiments are consistent and repeatable across observers and cultures. What changes is not the truth of the results, but the understanding of how those results come into being. Reality remains lawful and structured, but those laws govern probabilities and interactions rather than fixed properties alone. As this understanding deepens, it becomes clear that observation is not an isolated phenomenon confined to laboratories. In the natural world, interactions constantly play the role of measurement. Particles collide, fields fluctuate, and environments interact with systems, continually shaping outcomes. This process, often called decoherence, explains how the definite world we experience emerges from underlying quantum possibilities. Through countless interactions, possibilities are rapidly narrowed, giving rise to the stable, classical reality of everyday life. Yet even in this familiar world, the quantum foundation remains. The solidity of objects, the stability of matter, and the flow of energy all depend on quantum processes that involve constant interactions and selections. Observation, in its broadest sense, is happening everywhere, all the time. Reality is continuously being shaped through interaction, moment by moment. This perspective carries philosophical weight because it reframes the human role in the universe. Humans are not external spectators watching a cosmic performance from a distance. We are participants embedded within the same web of interactions that governs everything else. Our instruments, our bodies, and our environments are part of the same physical processes we study. When we observe the universe, we are the universe observing itself through a particular arrangement of matter and energy. There is something quietly humbling in this realization. It removes the illusion of absolute detachment and replaces it with a sense of belonging. Observation does not grant dominance over reality. It reveals our participation in it. The universe is not a static object to be inspected, but a dynamic process that includes the act of inspection itself. At the same time, this idea can feel deeply calming. If reality is shaped through interaction rather than rigidly fixed, then change and uncertainty are not signs of disorder, but natural features of existence. The world is not brittle, it is responsive. Outcomes emerge through relationships rather than isolation. This resonates with many aspects of human experience, where meaning and direction often arise through interaction rather than control. In science, this understanding has encouraged new ways of thinking about information, measurement, and reality itself. It has influenced fields ranging from quantum computing to cosmology, where the role of observation continues to raise profound questions. Even the early universe, long before observers existed in any familiar sense, is now understood through frameworks that account for quantum interactions and the emergence of definite structures from possibility. Ultimately, the role of observation in shaping physical outcomes does not diminish reality. It enriches it. Reality becomes a living process rather than a frozen stage. The universe is not indifferent to interaction. It is defined by it. Each measurement, each encounter, gently guides what is possible into what is actual. To sit with this idea is to accept that reality is not something simply revealed, but something continuously realized. Observation is not a spotlight shining on a finished scene, but a subtle influence that helps bring the scene into focus. In this view, the universe is not a cold mechanism running on predetermined tracks. It is a responsive, evolving whole, where interaction and observation are woven into the very fabric of what it means for something to be real. For most of human history, space and time were treated as silent stages on which the drama of the universe unfolded. Space was thought of as an empty container, stretching endlessly in all directions, while time flowed steadily and uniformly, the same everywhere and for everyone. Events happened within space and time, but space and time themselves were assumed to be fixed, passive, and unaffected by what occurred inside them. This view felt intuitive because it matched everyday experience. Rooms do not appear to change shape when someone walks through them, and clocks seem to tick at the same rate regardless of who is watching. Yet as physics pushed deeper into the foundations of reality, this comforting picture began to soften, revealing that space and time are not rigid backdrops at all, but active, dynamic participants in the structure of existence. The first major crack in the classical view came with the realization that measurements of space and time depend on motion. When scientists studied light and its constant speed, they discovered that distance and duration could not be absolute. Lengths could contract, and time could slow down, depending on how fast an observer was moving. This was not an illusion or a flaw in instruments, but a genuine feature of reality. Space and time adjusted themselves to preserve deeper physical laws. Already, the idea of a universal clock and a single, fixed geometry of space was fading. Quantum physics carried this transformation even further. At very small scales, space and time behave in ways that defy classical intuition. They lose their smooth, continuous character and begin to appear grainy, uncertain, and intertwined with the behavior of matter and energy. In the quantum world, particles do not follow neat paths through a well-defined space. nor do events unfold along a perfectly ordered timeline. Instead, positions blur, durations fluctuate, and the distinction between here and there, before and after, becomes less sharply defined. One of the most striking insights is that space is not truly empty. What appears to be a void is actually filled with quantum fields, constantly fluctuating with subtle activity. Even in the absence of particles, these fields vibrate with energy, giving rise to temporary events that flicker in and out of existence. Space is not a passive container holding matter. It is a dynamic medium with its own restless character. Matter and energy arise from this underlying structure, suggesting that space itself plays an active role in what exists. Time, too, reveals a deeper complexity. In classical thinking, time flows independently of events, marking change without being changed itself. Quantum physics challenges this idea by showing that time is closely tied to physical processes. At fundamental levels, it becomes difficult to define time without reference to change, interaction, and measurement. Some quantum theories even suggest that time may not be fundamental at all, but an emergent property that arises from deeper, timeless relationships. This idea is deeply unsettling to everyday intuition, yet it carries a strange coherence. If space and time are not fundamental, then reality is not built on a fixed grid, but on relationships. Events do not simply happen at points in space and moments in time. Rather, space and time are shaped by the network of interactions among physical systems. Distance becomes a measure of relational separation, and time becomes a way of describing how change unfolds within these relationships. In the quantum realm, particles can be entangled in ways that seem to ignore spatial separation altogether. Two particles can behave as a single system, even when separated by vast distances. This does not mean information travels instantly through space, but it does suggest that spatial distance is not always the most fundamental measure of connection. At a deeper level, entangled systems share a relationship that transcends classical notions of space. Space, in this sense, is not merely a divider, but a flexible expression of deeper connections. Similarly, quantum processes challenge the simple ordering of time. In certain experimental setups, it becomes unclear which event happened first. Cause and effect can appear blurred, not because logic breaks down, but because the underlying reality does not always conform to a single, well-defined temporal sequence. Time, rather than flowing uniformly from past to future, may behave more like a layered structure, where events are linked through probabilities rather than strict order. This does not mean that everyday time is an illusion. At the scales of human experience, time behaves reliably and predictably. The past feels fixed, the present immediate, and the future open. Quantum physics does not deny this experience. It explains how it emerges. Through countless interactions, uncertainties average out, and a stable sense of time arises. The familiar flow of moments is a collective effect, born from deeper processes that are far less orderly. Space follows a similar pattern. At large scales, it appears smooth and continuous, providing a reliable framework for motion and structure. At extremely small scales, however, space may be fragmented, fluctuating, and uncertain. Some theories suggest that space itself is made of discrete units, woven together like a fabric at the smallest possible scale. In this view, the smooth space we experience is an approximation, much like a calm surface that hides microscopic turbulence beneath. The idea that space and time are dynamic rather than fixed changes how we think about reality itself. Instead of imagining a universe where things happen within an unchanging arena, we are invited to see a universe where the arena and the actors are inseparable. Matter shapes space, interactions shape time, and the structure of reality emerges from this ongoing interplay. Nothing stands entirely outside the system. Everything participates in shaping the whole. This perspective also reshapes the concept of the present moment. If time is not a universal flow, but a local, relational phenomenon, then the now is not the same everywhere in the universe. Different observers can legitimately disagree about which events are happening simultaneously. The present becomes something personal yet still physically meaningful, defined by the observer's relationship to the surrounding world. Reality accommodates multiple perspectives without contradiction. At a deeper philosophical level, the flexibility of space and time invites a gentler view of existence. Change is not something imposed upon a rigid framework. It is part of how the framework itself evolves. Stability and impermanence coexist naturally. Structures form, persist for a while, and dissolve, all within a space, time that adapts and responds. There is no absolute reference point against which everything must be measured. This understanding also influences how scientists think about the origin of the universe. If space and time are dynamic, then asking what happened before the beginning becomes a subtle question. The beginning of the universe may not be an event within time, but the emergence of time itself. Similarly, space may not have expanded into something, but emerged as a set of relationships that grew and evolved. These ideas stretch the limits of language, yet they offer a coherent way to think about cosmic origins without relying on hidden absolutes. In everyday life, the idea that space and time are flexible rarely intrudes. We move through rooms, schedule our days, and trust our clocks without hesitation. Yet beneath this surface reliability lies a deeper truth. The stability we experience is an emergent feature, not a fundamental one. The universe is not built on rigid scaffolding, but on adaptable patterns that give rise to order through interaction. There is something quietly soothing in this realization. If space and time themselves are not fixed, then rigidity is not the essence of reality. Flexibility, responsiveness, and emergence are just as fundamental. The universe is not locked into a single, unchanging structure. It is free to evolve, to create new forms, and to explore new possibilities within the bounds of its underlying laws. As science continues to explore these ideas, the picture of reality grows less mechanical and more organic. Space and time behave less like empty boxes and ticking clocks, and more like living aspects of a coherent whole. They stretch, adapt, and respond, shaping and being shaped by the matter and energy they host. To reflect on this is to recognize that our everyday experience, while valid and meaningful, is only one layer of a much richer reality. Beneath the familiar flow of time and the apparent solidity of space lies a subtle, dynamic structure, constantly in motion. Quantum physics does not strip reality of meaning. It deepens it, revealing a universe where space and time are not silent witnesses, but active expressions of an ever unfolding whole. At the most fundamental level described by quantum physics, the universe is not made of separate, self-contained objects drifting independently through empty space. Instead, everything that exists arises from underlying quantum fields that extend everywhere. These fields are not abstract mathematical tricks. They are the deepest physical entities we know. Particles are not primary things, but temporary excitations, gentle ripples in these ever-present fields. This perspective quietly overturns the everyday idea of separation and replaces it with a vision of deep, invisible connection woven into the structure of reality itself. In classical thinking, matter appears as solid units with clear boundaries. A stone feels distinct from the air around it, and one person feels clearly separate from another. Quantum field theory softens this picture. According to this view, every type of particle corresponds to a field that fills all of space. The electron is not a tiny bead moving through emptiness. It is a localized vibration of the electron field. Photons are excitations of the electromagnetic field. Quarks arise from their own fields, and even what we call empty space is a sea of overlapping quantum activity. Nothing exists in isolation because the fields themselves are everywhere. This means that connection is not something added on top of reality. It is built into reality from the start. Every particle shares its origin with the same underlying fields that permeate the universe. When a particle appears, it does not come from nothing. It emerges from a field that already connects it to everything else. When it disappears, it dissolves back into that same field. Existence becomes a continuous process of emergence and return, rather than the motion of isolated objects through a void. Entanglement offers one of the clearest demonstrations of this deep connection. When particles interact in certain ways, their properties become linked so strongly that they can no longer be described independently, even when separated by vast distances. Measuring one particle immediately determines the outcome for the other. This phenomenon does not involve signals traveling faster than light, but it does reveal that the particles are part of a single, unified system. Their connection is not mediated by space in the usual sense. It is a reflection of their shared quantum state. This challenges the intuition that distance weakens connection. In the quantum world, connection is not primarily about proximity. Two entangled particles can be light, years apart, and still behave as one system. This suggests that space is not the deepest level at which reality is organized. Beneath spatial separation lies a more fundamental layer of relationships, where connections persist regardless of distance. Space, from this perspective, is an emergent feature that arises from deeper patterns of correlation. The idea of universal connection also extends beyond entanglement. Quantum fields interact constantly, even in what appears to be empty space. Fluctuations in one field can influence others, giving rise to forces and interactions that shape the behavior of matter. The forces of nature are not external pushes acting across empty gaps. They are expressions of field interactions. Attraction, repulsion, and transformation all arise from the way fields influence one another. Everything that happens is the result of these ongoing, invisible conversations. This field-based view of reality dissolves the sharp boundary between objects and their environment. In classical terms, an object is something with a clear inside and outside. In quantum physics, an object is better understood as a stable pattern within a field, maintained by continuous interaction. Its identity is not defined by isolation but by relationship. Remove the interactions that sustain it, and the object ceases to exist in its familiar form. This perspective has profound implications for how we understand individuality. If everything arises from shared fields, then absolute independence is an illusion. Each thing is a localized expression of a much larger whole. This does not erase individuality, rather, it redefines it. Individuality becomes a pattern of relationships rather than a self-contained essence. A person, like a particle, is a dynamic process shaped by countless interactions, not a fixed entity standing apart from the rest of reality. The interconnected nature of quantum fields also reshapes how we think about causation. Effects do not always travel through space as simple chains of influence. Instead, outcomes can reflect the global structure of a system. Changes in one part of a field can alter the conditions elsewhere, not through direct signaling, but through the shared framework of the field itself. Causation becomes less like a line of falling dominoes and more like a pattern that adjusts as a whole. This does not mean the universe is chaotic or lawless. On the contrary, quantum field theory is one of the most precise and successful frameworks in science. Its equations predict experimental results with extraordinary accuracy. The order of the universe does not come from isolated objects following fixed paths, but from the stable behavior of underlying fields and their interactions. Harmony arises from connection, not separation. The idea that everything is connected through invisible fields also sheds light on the nature of emptiness. What we call empty space is not empty at all. It is filled with fields in their lowest energy states, still active, still fluctuating. These fluctuations have measurable effects, influencing the behavior of particles and even the structure of the universe itself. Emptiness, in this view, is simply a quieter form of fullness. As this understanding deepens, the boundary between matter and energy becomes less rigid. Matter is condensed energy within fields, and energy is the activity of those fields. The famous equivalence of mass and energy finds a natural home in this framework. Everything that exists is a manifestation of field activity, taking different forms depending on how that activity is organized. This vision of reality carries a subtle emotional resonance. If everything arises from shared fields, then separation is never complete. Even the most distant objects are linked through the same underlying fabric. The universe is not a collection of disconnected pieces, but a single, continuous process expressing itself in countless localized ways. Each part reflects the whole, not metaphorically, but physically. There is a quiet elegance in this idea. It suggests that the complexity of the universe emerges from simplicity at a deeper level. A few fundamental fields, governed by consistent principles, give rise to the immense variety of forms we observe. Stars, atoms, and living beings are different expressions of the same underlying reality, shaped by different patterns of interaction. In everyday experience, this deep connection is hidden by scale. At human scales, interactions average out, and objects appear separate and stable. Quantum physics does not deny this appearance, it explains it. The solidity and independence we experience are emergent properties, useful and real at our level, but not fundamental. Beneath them lies a world where connection is primary. To reflect on this is to see reality less as a collection of things and more as a web of relationships. Existence becomes an ongoing conversation among fields, a continuous exchange of influence and information. Nothing stands entirely alone, and nothing exists without context. In this light, the universe feels less like a cold, fragmented expanse, and more like a coherent whole, quietly unified beneath its surface diversity. Quantum physics does not merely tell us that things interact. It reveals that interaction is the very essence of what it means to exist. Everything that is connected, not by metaphor or philosophy alone, but by the invisible, ever-present fields that give rise to all of reality. When the universe is viewed through the lens of quantum physics, it no longer resembles a rigid machine made of solid parts, grinding forward in time. Instead, it appears as a calm, unfolding process, guided by probabilities, interactions, and gentle transitions rather than fixed gears and predetermined outcomes. This shift in perspective does not strip the universe of structure or lawfulness. It softens our understanding of how order arises. Reality becomes less about mechanical certainty and more about continuous emergence, where change is not forced but naturally expressed through the fabric of existence. In the classical world, nature was often compared to clockwork. If one knew the position and motion of every component, the future could, in principle, be predicted with perfect accuracy. This image was powerful and comforting because it promised total control and complete understanding. Quantum physics quietly revealed the limits of this metaphor. At the smallest scales, the universe does not behave like a set of gears turning in lockstep. It behaves more like a field of possibilities, where outcomes arise through interaction and probability rather than strict determinism. This does not mean the universe is chaotic or random in a crude sense. Quantum processes follow precise mathematical rules. What changes is the role of certainty. Instead of exact predictions for individual events, quantum physics offers reliable predictions for patterns and tendencies. The universe does not commit to a single outcome until interaction occurs, and even then, the outcome is selected from a range of possibilities. This creates a sense of gentle unfolding, where the future is not fully written but gradually takes shape. At every moment, countless quantum events are occurring, each one a small transition from possibility to actuality. These events do not happen in isolation. They are woven together through fields, interactions, and relationships that give rise to stable structures. Atoms form, molecules assemble, stars ignite, and galaxies evolve, all through processes that balance uncertainty with order. Stability emerges not because the universe is rigid, but because its underlying dynamics naturally favor certain patterns over others. This view changes how we think about change itself. In a mechanical universe, change is something imposed, driven by forces acting on passive objects. In the quantum universe, change is intrinsic. Systems evolve because interaction is fundamental to their nature. Nothing is truly static. Even what appears still is supported by constant activity at deeper levels. The calm unfolding of reality is not the absence of motion, but a balanced flow where transitions occur smoothly and continuously. Time within this framework feels less like a ticking clock and more like a rhythm. Events do not march forward in perfect synchrony, they arise when conditions allow. The future is not a rigid sequence waiting to happen, but a landscape of possibilities gradually narrowing as interactions occur. This lends a sense of openness to existence. The universe is not rushing toward a predetermined end. It is exploring what can emerge within the constraints of its laws. This openness does not undermine meaning or coherence. On the contrary, it allows complexity and novelty to arise. If everything were fixed from the beginning, there would be no genuine emergence, only the unfolding of what was already implicit. Quantum physics suggests that while the rules are stable, the outcomes are not fully specified in advance. New structures, behaviors, and patterns can arise that were not explicitly encoded at the start. The universe is creative in a quiet, lawful way. The calm, process-oriented nature of reality also reshapes how we think about causation. Causes do not always produce effects in a rigid, one-to-one manner. Instead, causes influence the range of possible effects. An interaction sets the conditions under which certain outcomes are more likely, but it does not dictate a single result. This gentler form of causation aligns well with the complexity we observe in natural systems, where small influences can have subtle, context-dependent effects. At larger scales, this quantum openness is often hidden by averages and collective behavior. Billions of microscopic events combine to produce stable, predictable patterns. A rock falls, a planet orbits, a heartbeat repeats. These regularities are real and reliable, but they are emergent. Beneath them lies a sea of tiny uncertainties that cancel and balance one another. The apparent solidity of the world is the result of this balancing act, not evidence of a fundamentally rigid universe. This understanding also invites a different emotional relationship with reality. If the universe is a calm, unfolding process rather than a harsh machine, then uncertainty is not an enemy. It is a space where possibilities live. Not knowing exactly what will happen is not a failure of understanding, but a reflection of how reality itself is structured. This perspective can foster patience and humility, recognizing that control has limits, and that emergence plays a vital role in how things become what they are. The idea of a non-mechanical universe also influences how we think about life and consciousness. Living systems are not rigid mechanisms. They are adaptive, responsive, and creative. They maintain order not by resisting change, but by flowing with it. Quantum physics does not explain life in simple terms, but it provides a backdrop that makes life's flexibility feel natural rather than anomalous. A universe built on gentle unfolding is a universe where complex, responsive systems can arise. Even at the cosmic scale, this perspective holds. The evolution of the universe, from its earliest moments to its present structure, reflects a balance between law and openness. Physical constants set boundaries, but within those boundaries, rich structures emerge. Stars form, burn, and fade. Galaxies collide and reshape. Nothing is frozen in perfection. Everything participates in an ongoing process of transformation. This process-oriented view also reshapes how we think about endings. In a mechanical universe, an ending can feel like a breakdown, a failure of the system. In a universe of unfolding processes, endings are transitions. Structures dissolve, but the underlying reality continues, giving rise to new forms. Nothing is truly wasted. It is transformed. This aligns with the quantum understanding that particles and fields are constantly appearing and disappearing, yet the overall structure remains coherent. There is a quiet wisdom in seeing the universe this way. It suggests that stability and change are not opposites, but partners. Order does not require rigidity, and freedom does not require chaos. The universe finds its balance through lawful uncertainty, allowing patterns to form without locking them into permanence. As this understanding deepens, the metaphor of the machine gradually loses its hold. The universe is better understood as a living process, not alive in a biological sense, but alive in its responsiveness and creativity. Reality is not something that simply is. It is something that happens. Each moment is a gentle transition, shaped by what came before, but not fully determined by it. To rest with this idea is to see existence as an unfolding story rather than a fixed script. The laws of physics provide the grammar, but the sentences are not all written in advance. The universe speaks itself into being, moment by moment, through interaction, probability, and emergence. In this light, reality is not cold or indifferent. It is calm, structured, and open, inviting participation rather than demanding control.